right. So now we have Angela Zhou. She's graduated from Cornell and is actually joining USC. And she works in combination of statistical learning and object research, and she will talk to us about robustness and causal inference.
All right, thanks. I'll be talking today about robustness and causal inference. The first part is going to be about global robustness, so optimization, where we want the interpretation that we're being robust over a set. So we're going to talk about the interface of causal inference and decision making. This talk will be focused more on causal inference, but we're going to see elements of various talks from earlier today about the interface with decisions, and in particular sensitivity analysis or perturbation analysis. So the second part of this talk is going to focus more on local robustness or sensitivities and building connections from local perturbations in order to recover more standard bias adjustments or doubly robust estimators for causal inference in the absence of unobserved confounders. So the first part is going to focus on a particular challenge of unobserved confounders, and the second part is going to be more general for causal inference with local robustness rather than global robustness. So to motivate global robustness, we provide a high-level overview of the problem, and I'll talk more about the causal inference framework, because that causal inference is very causal assumptions in, causal inference out. We kind of generally understand that these assumptions are never true, but optimization provides a perfect kind of analyst-driven framework in order to provide estimation frameworks for the realistic setting where robustness is helpful, where these assumptions are always untrue, but optimization helps us be robust to mild or moderate violations. And so I'm first going to talk at a high level about this off-policy policy learning problem and draw some analogies to classification or other kinds of decision loss formulations that you might be more familiar with before I make the formulation and the notation more precise. So the motivation or the causal inference setting might be that you have a large medical database. All of your rows are the outcomes of individual patients. You measure information about the patients, contextual information, covariates X, and you observe the actions that doctors took in this data set, here denoted as A, where 1 is treatment and 0 is control. And now the causal inference challenge is that for every individual, you only observe the causal outcome for the treatment that was administered. So you care about both causal outcomes. But what this means is that the data that you work with has this fundamental missingness challenge. And so now if you want to evaluate a different clinical decision rule that differs from, on average, how patients were being treated, you don't actually know what were the true causal outcomes for individuals who weren't treated, or if now your recommendation differs from what the doctor had previously given, you don't actually know what that alternative would have been. Now, of course, there's been a lot of work on causal inference, which develops statistical frameworks to impute these counterfactual causal outcomes. They account for the particular challenge of confounding. So causal inference is an inherently decision-theoretic framework because it posits that every individual has a pair of random variables. And if you're making decisions, you're concerned with optimizing your choice of these random variables. But it's additionally concerned with the statistical challenges of confounding. So intuitively, confounding can arise in this data situation if doctors were giving treatments to patients based on their estimation of initial severity. So if the treatment was being reserved for the patients who are worse off, and now we try to learn a naive regression model in the subset of individuals who are worse off to begin with, we may wrongly attribute that the patient deterioration is due to the treatment, rather than recognizing that this is due to the association between treatments and outcomes in our original data set. So that's statistical confounding, but this work is going to focus on the challenge of unobserved confounders. And so what is the specific decision-theoretic setting that is different from just normal causal inference or just normal machine learning? And so it's this problem of off-policy policy learning from observational data in the middle. And so it's useful to think about two comparisons. The first is on the left, traditional causal inference, where we would simply choose between treating everyone or treating no one. And the most, what we want to estimate in order to inform that course decision is just the average treatment effect. In contrast, if we believe that individuals' treatment outcomes actually differ based on their covariates, if we believe that there's heterogeneity in the underlying causal responses, then we can improve by personalizing our decisions. So this cartoon is just a decision policy to keep in mind. It's a classifier that would map an individual's covariates to which treatment they should receive. And so the setting on the right might look more familiar to machine learning. If you had a data set with all of the counterfactual outcomes for every individual, you could compute which treatment was better for every individual, and you could just learn a classifier on this data set from the right-hand side. Except you would want your classifier labels to be weighted by the causal effect of which treatment is better. And so you can think about this as cost-sensitive classification if you knew all the information. And so the challenge is that we're exactly working with a setting in the middle where you don't know all of the information and you actually want to impute it with these statistical causal inference methods. And so just to provide an example of why unobserved confounders are more often the case than not, there's the historical example of the Women's Health Initiative, which ran a parallel clinical trial and observational study. So in a clinical trial or an A/B test or a randomized experiment, you have no confounding because treatment is assigned completely at random. So it's independent of everything. In contrast, in the observational study, they just surveyed 48,000 women and they asked them, did you ask your doctor for this treatment? But there could be a lot of additional unobserved information that informs whether or not a person sought out this treatment from the doctor and their eventual health outcomes. And so the story of this parallel trial is quite dramatic because we have a decision-theoretic reversal in the implications from the observational study and the clinical trial. The observational study suggests that marginally or on average, there's a 40 to 50% reduction in heart attacks. The clinical trial, the treatment was actually stopped early due to an increased incidence of heart attacks. So you have the opposite sign from the average treatment effect. Maybe there's benefits from heterogeneity. There could be subgroups based on age for which this treatment is beneficial. And so if we can personalize, we can maybe do better. And so this is an example. We're going to revisit this data later on. Nice methodological opportunity. And so just a reminder, an unobserved confounder, it's some omitted variable that affected both the treatment and the outcome. And so in this case, it could be something like health consciousness. How likely is a person to seek out these kinds of elective treatments, which then is correlated with how often they partake in other kinds of preventive health activities. Okay, so I'll start with the problem setup and background, connect back to traditional causal inference and show how you can rewrite this kind of problem as a kind of adversarial or robust classification problem, which may be more familiar to machine learning. Talk a little bit about how the optimization interacts with the theoretical guarantees. And I'm going to try to describe this at a high level so you can see how we can use the same ideas to tackle much harder estimation problems like infinite horizon reinforcement learning. So just to describe the notation and fix ideas, I'm going to assume that your database or observational data set consists of these triples of random variables, these covariates X, observed treatment A, and the outcomes Y, sorry, they're loss outcomes, so lower is better. The causal inference framework, it's called potential outcomes. That's terminology, but you can think about it as assuming that every individual is endowed with a random vector of outcomes for every value of treatment, and you only get to observe one of them. The main assumption that we're focused on relaxing is that of unconfoundedness. So it assumes that the potential outcomes are conditionally independent of the treatment assignment, conditional on observed variables X. Intuitively, this is like saying that you assume you've measured all of the information that accounts for both the treatment assignment and the outcome. And this is essentially the workhorse assumption that makes the rest of causal inference work, because to summarize at an extremely high level, a lot of the statistics is about focusing comparisons, conditional on some covariates, so that you end up comparing people with who were as if randomized to different treatments. And so this is really what makes a lot of the statistical methods for causal inference work. So I'll spend some more time to introduce the elements of causal inference for decision making that you would be concerned about, or that you'd be concerned in estimating under the assumption of unconfoundedness, before talking about the exact estimation procedures and how that leads to our robust approach. So the conditional average treatment effect is the covariate conditional contrast in the potential outcome conditional expectations. Under the typical assumptions, you can estimate this by regression, and you can recognize that the average treatment effect is just a marginalization of these conditional contrasts. For the specific policy learning setting, the policy pi is going to be a personalized decision rule. So you should think about this as a probabilistic classifier. It maps an individual's covariates to the probability that they should receive treatment. And you ultimately want to optimize over the space of classifiers. So functional parameterizations that you might consider are linear indices. So an integer variable dependent on a linear index. And so that can be written as a mixed integer program, or logistic probabilities, or decision trees, which you can also write as an integer programming formulation. And so now the way that we evaluate the quality of a policy is called a policy value. So it's the population expectation of the causal outcomes that would be induced had you assign treatment according to this decision policy pi. So you end up statistically estimating the element of this expectation. For robustness purposes, we're going to consider the policy regret against a fixed baseline pi naught. Okay, and in analogy to machine learning, you can proceed with a couple of ways to go from estimation of causal effects to decisions. The first is based on regression estimation. And so presumably, if unconfoundedness were true, you simply learn regression models of the treated and untreated individuals, take differences, and then treat based on the decision boundary implied by these regression models. But now, if you used complex machine learning models in order to avoid issues of selection bias, your decision boundary is the complex difference between two deep neural networks. And so that can be uninterpretable, unstable, and so on. This approach, the other approach we're going to focus on is on policy learning, which is much more about a weighted classification approach. And so I won't go into details on the comparisons. And so at a high level, what we're going to do is we're going to focus our attention on how the statistical estimator depends on the unknowns, or what we want to be robust against. And so what's really important is that we don't care, for the purposes of statistical estimation, about the complex relationship between observed covariates, unobserved confounders, and the outcomes of the treatment. That's a lot of different conditional relationships, but we actually only care about this one-dimensional projection of the observed and unobserved confounders onto the treatment, or the so-called propensity score. And so this is a pretty classic result in causal inference, that this is all you need to estimate causal effects. And so having identified the right representation of what the statistical estimator depends on, we're going to parameterize an uncertainty set and assume that we can specify an ambiguity set for where our unknowns, in particular the inverse probability weights, which we're going to call beta for behavior policy, where they live relative to what we can estimate from the data. And then we're going to build an analogy to adversarial machine learning. So for a fixed policy, or for a fixed classifier, we can evaluate the worst case value of this estimator. And of course, we can also optimize over the space of policies, or over the space of classifiers, to find a classifier that achieves the best worst case regret. So the main technical challenge, which I'm going to gloss over, is about ensuring the valid statistical performance when we're optimizing over ambiguity that can vary arbitrarily for every data point. So I'm going to proceed to fill in the details, but this is the high-level recipe. And for harder decision problems, I'll talk about how you can change different aspects of these specific components. But we're going to start with a classical estimator for a causal inference based on inverse propensity weighting. Here is the reduced dependence on the unobserved confounding. If we observed everything, both observed and unobserved covariates, then we could just use a typical estimator, which uses the propensity score or the probability of human assignment to change measure from the confounded measure to the population measure. So think about this as a distribution shift problem. And so we simply need to consider this important sampling weight. Of course, in our setting, we don't observe the unobserved confounders, and we don't know how pi b depends varies in U. What we're going to do is we're going to work with a specific uncertainty set from causal inference. This is more for translation purposes back to causal inference. Once you write it as an optimization problem, you can, of course, specify additional arbitrary constraints. But you can think about this as a max restriction on how far the unknown, a long conditional probability, beta, depends or deviates from what you can estimate from data. So you can always estimate pi b of A given just observed covariates from data. This is just now insufficient to completely debias your data. But based on this assumption, you can relate your unknown to what is known but biased. And now you can just translate this into a pointwise interval set for optimization. And so just to plug back in these specific components into the recipe I described before, the core of the method is that our empirical regret estimate for a fixed policy pi is going to optimize our estimate of the regrets over this choice of uncertainty set for a fixed radius. And then we're going to find a confounding robust policy by solving this kind of min-max problem. I won't go into too many details about the algorithms. You can solve the integer program depending on your choice of policy parameterization. You can also follow a recipe from adversarial machine learning where you you run a subgradient method. And that is, of course, non-convex, but it works reasonably well in practice. So the main special aspect here is the interaction between the optimization characterization and what you can show about the convergence, the statistical convergence of the entire procedure. So this is a statistical result about the rate at which the population regret of the estimated policy converges to the population regret to the population optimal policy. And you can obtain this, but you required some control that you were ultimately optimizing over a set of functions that had a VC dimension. And so it was not obvious from its face that if you write down an optimization function that scales in the size of the data set, that this is so. But it turns out that that pointwise uncertainty set, and additionally, if you add an L1 norm budget, you can also show that they have sufficient enough structure that you can show that there's a finite VC dimension. Okay, so I'll talk about the case study just to kind of show how these policies perform in practice. And so we're going to revisit the data from the observational study in RCT. And we're going to consider a set of semi-synthetic outcomes where we simply add some treatment effect bonus. And let me describe the comparisons for a for one of these data sets before showing you the comparison for more of them. And so on the x-axis, we have the size of the uncertainty set. And so what we do is we're going to increase the size of the set that we're optimizing over. We're going to train them on the observational data set, the confounded data set, and we're going to evaluate the regret out of sample on the randomized controlled trial. And in the blue line is the robust version with a logistic parameterization, and in red is IPW, or the non-robust version. And what we can see is that because the 0 is the dashed gray line and the y-axis is the policy regret achieved against control, is that the gap between the dashed line and the blue line is indicative of improvement, and between the red line and the dashed line is safety. So if we wrongly assume unconfoundedness when it's not true, we're going to end up treating everyone. And in contrast, the robust policies are only going to treat subsets of the population who would be assured beneficial regrets, regardless of some size of the confounding. And so the summary is that overall, we improve uniformly, and when we can improve, there are reasonable regions of improvement. So I'm going to describe an extension or a follow-up to a much harder decision problem, that of infinite horizon reinforcement learning. And so in this setting, it's a different problem setting because we're assuming we have offline trajectories of sequential data, in particular infinite horizon reinforcement learning. So one example is diabetes management, which is a much more long-term management problem. And there are PID controllers for the management of blood glucose. And this is typically a continuous monitoring problem. So you may revisit similar system states at similar times of day and so on. And so in these situations where you don't have the capacity to run new randomized data, it's quite often that you didn't have control over your data collection environment. And so you're also concerned about unobserved confounders in a much more difficult continuous monitoring setting. And so I described this high-level framework where you start with a statistical estimator. And so what we're going to do is we're going to show how if you change your statistical estimator, impose some structural restrictions, you can repeat similar methodological approaches to derive a way to obtain robust bounds. And so let me briefly walk through how these structural restrictions are different, just to illustrate how you can apply this to more complex situations. So we're going to model this as an MDP on a joint state space of observed discrete states and U of unobserved confounders. It's going to be a Markov decision process on this joint state space. The reward is only a function of your observed state, but the main restriction is that the unobserved confounders are going to be kind of assumed to be generated independently at every time step. So this isn't going to be fully general. Again, you want to, you assume that there was this full information trajectory, but you have this censored observation. And this assumption that of the unobserved confounders being ID generated essentially allows us to relate what we can control or estimate from the data back to a space of MDPs on this latent space of unobserved confounders. So the main difference is that we're going to work with importance sampling in the space of stationary distributions. So in this infinite horizon setting, what's nice is that all our expectations are linear with respect to stationary distributions. We're going to focus on importance sampling in the space of stationary distributions, in contrast to the product of importance weights or importance sampling in the space of trajectories over time. So these stationary distributions are the time limit of how often you visit certain state action next state tuples. And you can marginalize that joint distribution to your distribution over the states. And you can further marginalize that to just your distribution over the observed states. And so what you observe in your data is the stationary distribution on just the observed states under the behavior policy. But again, that's going to be insufficient to debias your data, and that'll lead to biased estimation of the transition probabilities. And so again, we're working with these objects because our policy value is linear in the space of stationary distributions, and it's linear in the space of density ratios. So the main object of interest is the density ratio of the stationary distribution that will be induced by our new policy. You don't know that policy because you can't run the policy, but you do observe the stationary distribution of just the observed states. Okay, so those are the structural restrictions. The estimator is building on a paper from Liu et al. 2018. And essentially, you can show that under these assumptions, we've identified an estimator where if only we knew the realizations of the unobserved confounders, then we could recover the quantity that we need for estimation. And of course, this is the point where we simply reuse the ambiguity set to now optimize over the range of density ratios that solve this estimating equation in order to evaluate the range of policy value estimates that this implies. So at a high level, this is what we do. There are some details on the reparameterizations and so on. And so the prescription is to just solve this optimization problem. Unfortunately, it's computationally much more difficult. Nonetheless, Garobi can solve this for small instances, and you can build upon this characterization to obtain computational relaxations. And so you can run this for small instances, but because the optimization problem is non-convex, our statistical understanding is less well developed. Okay, so that was the case of unobserved confounders. I'm now going to talk about ongoing work on empirical Gateaux derivatives for causal inference. So the problem setup is going to be different because this is more about recovering bias adjustments for causal inference using robustness or using influence functions. So I'm first going to have to describe some motivation before talking about our characterization, before we can actually revisit the infinite horizon problem to derive a doubly robust estimator from these local perturbations. And so to summarize, the past several years of interest in machine learning and causal inference, we would like to use black box machine learning for causal inference, but we would also really need confidence intervals and valid convergence. The nice thing about causal inference is that there's a framework to describe the fact that we are targeting certain summaries of the distribution rather than wanting to recover the full distribution. So the average Freeman effect is a certain kind of functional. It is not the entire distribution. And because the causal inference framework has some restrictions, namely these conditional independencies, that's why we can derive these bias adjustments that allow for debiased or doubly robust estimators. And so we can typically reduce the first order bias that arises from machine learning because of the structure from causal inference. And now these debiasing adjustments in the most general framework, they're the average of influence functions. But unfortunately, deriving these influence functions often requires special training. So the way it currently works is that you hire a grad student, you train them for 3 or 4 years to derive, to learn how to derive these influence functions and so on. And then you can derive influence functions for new specific applications. On the other hand, to kind of speak loosely or imprecisely, to be kind of suggest, these influence functions, they are just Gateaux derivatives in a special direction. And so a key question is, can this process of deriving these orthogonal adjustments be computerized or made more algorithmic or computerized so that we're not just deriving them by trial and error, which is how they're typically done in practice. And so we're going to build on a line of recent work that proposes or studies computing these derivatives by finite differences. We're going to focus on the interaction between estimation and computation. And so we're going to detour through nominal causal inference so that we can derive double robustness with the perturbation analysis of optimization programs deterministically. So, and this is really motivated at a high level by recognizing that there's this gap between the computational expressivity that we have with constraints. So when we put things in the optimization framework, it becomes much easier to specify arbitrary constraints. In contrast, the current state for deriving doubly robust estimators with constraints essentially requires your optimization problem to have a closed form solution. And so there's this gap between our ability to obtain statistical benefits versus our ability to computationally solve these problems. And so to introduce some of the statistical machinery we'll need, the main idea is that we can consider causal inference estimates as statistical functionals of distributions, which are summaries of the distribution. Like the mean is a functional, and we can use the characterization of sensitivity of these functionals to distributions to describe these bias adjustments. So for example, back to the case of causal inference, the mean under missingness is of course the average of these conditional expectations. And of course, that's a particular integral. We're going to have to work with the integral representation quite often. And to introduce a little more machinery, the influence function is the Gateaux derivative, which is a scalar derivative of the functional when we perturb it in the direction of a distribution. And the influence function is a particular choice of which distribution that we use to perturb it with. And influence functions, kind of dating back to Hampel and Huber, we have this nice natural qualitative sensitivity analysis interpretation. So in recent years, they've been of great interest in machine learning to describe the stability of estimators. But so far, this qualitative sensitivity analysis or perturbation interpretation of influence functions is not used in causal inference at all. So you can describe many estimators in causal inference as actually you take the plug-in estimation of the functional and you add on the average of the influence function. So for example, the typical doubly robust estimator exactly takes this form, where you would start with an outcome model and then add on the reweighted residuals. To be more specific about the related work, some related work has indeed proposed deriving these estimates not from analytical computation of these derivatives, but from finite differences. There are some details or some wrinkles along the way. This analogy is correct for discrete distributions, but there's some technical issues for continuous distributions. So instead of perturbing in the direction of a Dirac delta function, you need to, in general, smooth that distribution. How are you going to smooth the delta function? Well, you can use a kernel function, like in machine learning. And so essentially, you have two sources of error from this finite difference approximation scheme. You have epsilon, a finite difference approximation error, and lambda, which is an error due to smoothing, which is more about the maintaining technical regularity. And so the key research questions here are to, one, try to understand how is it that the empirical Gateaux derivative approximates the numerical derivative, and understand what are the interactions between the computational rates of approximation with the statistical benefits. So what do we mean by empirical? Well, previous work has studied the finite difference approximation, but they've assumed that all the distributions that you plug in are essentially known. And so obviously, if you want to use this for estimation, you also need to estimate these distributions. And so much more concretely, the question is, how does the finite difference approximate what we know to be true, the analytical Gateaux derivative? So we know that calculus is correct, but it's still useful to have an understanding of exactly how this approximation works. And the key observation is that your choice of density estimates and estimating the distribution is going to induce the various conditional expectations and conditional probabilities that you would see in the more familiar form. And so that's nice because you can essentially use that knowledge to study the convergence probabilities. So just as a reminder of the nice properties of doubly robust estimation. So why is it that we need these kind of debiased estimators in order to obtain the nice benefits of machine learning and causal inference and get the best of both worlds? Well, for example, often these influence function adjustments have a mixed bias property. So you need only one of the outcome model or the propensity score to be well specified. So if you ran a randomized controlled trial, you exactly know the propensity score, which means that you don't need to well specify your outcome model. You also obtain benefits in convergence rates. So you can obtain the optimal rate of convergence for the functional or the the decision-theoretic summary that you care about with weaker convergence rate conditions on the individual nuisance functions. And so this can enable non-parametric estimation and can enable non-parametric estimation because black box machine learning is generally not going to have the same rates of convergence as parametric estimators. And so again, typically these kinds of adjustments are derived by either an analytical framework that so far has been kind of specialized, or otherwise by guessing and checking these various forms. Okay, so to relate this finite differences to what we are familiar with in terms of the doubly robust adjustment, we're essentially going to identify a couple of intermediate quantities. And so the first idea is that of a lambda smooth nuisance function. So this lambda smooth nuisance function essentially posits that instead of evaluating a regression function at x0, you are smoothing around the evaluation point. And this smoothing arises from the technical conditions. An epsilon perturbed nuisance function means that we're just going to analyze the difference between the regression model that is induced from our perturbed distribution estimate. And so again, what is nice about being so concrete about how the numerical derivative is related to what we are familiar with is because we know that what we're familiar with, the doubly robust adjustment, exactly enjoyed these beneficial improvements in convergence rates on the nuisance functions. So this level of concreteness is essentially what allows us to read off the approximation error requirements or approximation rate requirements on the approximation error requirements epsilon and lambda. They essentially need to converge faster than the statistical rates of convergence, which were weaker. Now, this characterization is still a little more curiosity driven rather than completely sufficient to completely prescribe the algorithmic approach. But this is still an illustration of interactions between statistical and computational approximation. Okay, so to return to this case of infinite horizon off-policy reinforcement learning, what's nice is that we can provide a doubly robust adjustment that reduces to black box evaluations of the optimization functional, which means that we're always going to be feasible. So our starting point is going to be a different characterization of the value function. So this primal dual pair is a very classical linear programming formulation for Markov decision processes. It can be considered like a variational characterization of the value of the optimal value function. And these dual variables, mu describes the state occupancy probabilities at optimality under the optimal policy. And so what we show is that if you evaluate these optimization problems, and if you plug in the perturbed estimates of the transition probabilities and the perturbed initial state distribution, you can one, use the deterministic analysis of optimization problems to derive a doubly robust influence function. So this additive term here on the right is, you can recognize that as a reweighted Bellman residual. And that first term is the plug-in regression estimate, the value function that is induced from this transition matrix. And so that's the analytical Gateaux derivative. It's not surprising because we know that the sensitivities are the dual variables, but for epsilon, but we can also study the finite difference. And we can again see that the finite difference differs from the analytical derivative based on these epsilon perturbed nuisances and so on, and we can derive the approximation error. But what's nice is that, again, everything we evaluate to compute this derivative is feasible, whereas if you plug in a doubly robust estimator back into the optimization problem, you can be infeasible in finite samples quite easily. Okay, so I'll stop there. We talked about causal inference and a different triangulation of decision-theoretic estimates, machine learning, and optimization. The first part was about using optimization to develop custom estimators for robust causal inference. The second was more about building connections between local perturbations to recover quite classical bias adjustments for all of causal inference.
Thank you. We have some time for questions.
I'm curious about the first part of the talk, the marginal sensitivity model, right? Because this is the sort of like, I guess, like uniform bounds, but there's like not too much confounding anywhere. And I'm curious if you have, I don't know, some sense of how that works out. Like empirically, like I would be worried about settings maybe where there's like not so much confounding in like many places, but like I want to count confounding in just like specific regions of the feature space or something like that, or generally how you think about like framing those uncertainty sets.
Yeah, absolutely. So I think it's exactly right that people may have other kinds of domain knowledge about the confounding, and it is very easy to add those domain knowledge or constraints from this perspective of just deriving optimization sets of where the weight function lives relative to this other value. So you can definitely define different classes of constraint sets. You can, and I think an interesting perspective is to think about learning implicit constraint sets that analysts may have in mind. So you can also imagine a kind of online procedure where you show them different sets and an analyst can provide a like rejection or a membership oracle for do they worry about this confounding or not? And so I think that's a very interesting perspective and it's more realistic. And that's definitely something that's much easier to, it's immediate in the optimization framework. Showing the regret bounds for these sets of constraints does so far require case by case analysis.
So in your uncertainty set for the inverse propensity weight, how do you make sure that those worst case weights are consistent with the observed distribution?
Yeah, so in terms of consistency with the observed distribution of the data, there is a part of the uncertainty set that cannot be informed from the data, which is related to like the radius or the size of the set. What can be informed from the data is that the inverse weights are a valid probability distribution. So I glossed over that detail in this description, but you can inform that with this kind of marginal constraint. You could also ask for a conditional constraint, but you run into finite sample trade-offs with the conditionality of that restriction.
So you make sure that they are like valid probably.
Yeah, up to a conic relaxation, which is part of the details, but yeah.
All right, let's thank Angela again.